In this video, we're going to cover the theory behind the different practicals in A-Level Chemistry. This video is designed to help you when approaching exam questions on these topics, as opposed to preparing you to do the practical as part of the practical endorsement part of the qualification. The first practical we're going to look at is titration. There are two parts to this practical. There is making up the standard solution and carrying out the titration. To make up a standard solution, weigh the bottle containing the solid you're going to make the standard solution of, transfer that to a beaker and reweigh the sample bottle. By recording the difference in the mass, you'll know precisely how much you have added. Then you're going to add 100 centimetres of distilled water to the beaker. Use your glass rod to stir it until your solid has been completely dissolved. You then pour your solution into your volumetric flask using a funnel to make sure none of your solution runs down the side of the volumetric flask and doesn't make it in. You'd then rinse the beaker you dissolved the solid in, and you'd add the washings of that into your volumetric flask. This makes sure all of your dissolved solid has been transferred from the beaker into the volumetric flask. You would then make up your solution to the mark on the volumetric flask with distilled water, using a dropping pipette for the last few drops to make sure you didn't go over the line. If you go over the line, you'd have to remake your solution. If you removed any volume from the volumetric flask, you're altering the desired concentration, as you'd be removing some of your dissolved solid as well as the solution. You'd then put the lid on the volumetric flask and invert it several times to ensure that you've got a uniform solution. So that means that all of your dissolved solid is evenly distributed throughout the volumetric flask. Sometimes you might calculate the known mass of the solid in the weighing bottle by transferring it to a beaker and washing the beaker several times to make sure that everything has been transferred. For the titration part of the practical, you want to make sure you've set up a burette and a clamp stand with a conical flask and a white tile underneath it. To start off with, you'd need to rinse all your equipment: the burette with the acid that you're going to use, your pipette with the alkali, and your conical flask with distilled water. You'll use your pipette to transfer 25 centimetres cubed of the alkali into the conical flask. You'll touch the surface of the alkali with pipette, and that means any alkali remaining in the pipette will be transferred to your conical flask. You'll then fill your burette with the acid, making sure the jet space, which is the space around the tap, is filled with the acid. You could get an incorrect reading if you do not do this. You then record your initial burette reading, so the volume shown on the burette, and add some indicator to your conical flask. Using a white tile underneath your conical flask will help you observe the colour change taking place. You'll then add the acid to the alkali, swirling as you go to make sure the two are mixing together, and then you'd add dropwise near the end point. If you're not sure where the end point is, you might have done a rough titration first, so you had some idea at which point you should be adding dropwise instead. You stop adding the acid when the relevant colour change, depending on the indicator that you've been using, is observed, and you then record the final burette reading so you could calculate the total volume you have added. You should repeat the titration until you have at least two concordant results, which is two readings within 0.1 centimetres cubed of each other. Some points to be aware of with this practical are that if the jet space, so the space around the tap, is not filled properly, you'll obtain a larger than expected reading, as the alkali or the acid is moving into the jet space first, which is obviously increasing the reading you're receiving, before going into the conical flask. We use conical flasks as opposed to beakers, as they are easier to swirl. Indicators are usually weak acids, so we only need to add a few drops of them. If we add too much of an indicator, it could affect the results of titration, as we're adding acid which wasn't intended to be there. If we're using phenolphthalein, that is pink in alkali and colourless in acid, so at the end point the pink colour will just disappear if we're using sodium hydroxide. Methyl orange is another indicator you could use. It's yellow in alkali red in acid, so the endpoint is when it appears orange just before it changes colour. That is if hydrochloric acid is used. There are two different methods we can use to measure an enthalpy change. In this case, you'd start by putting a polystyrene cup in a beaker for insulation and support. You'd then transfer the liquid reagent into the polystyrene cup, and you clamp a thermometer in place, making sure the bulb of the thermometer is immersed in the liquid to get an accurate temperature reading. You'd need to measure the initial temperature of the solution. If you're mixing two solutions together to get an enthalpy change, you'd need to measure the temperature of both. You'd then transfer your second reagent to the polystyrene cup and start the stopwatch. You would then need to stir both solutions so they are mixed together, and you'd then measure the temperature at regular intervals. Once you've completed your measurements, you then plot a graph of the temperature against the time, and you can then use the graph to extrapolate back from the cooling curve to the time at which they were mixed to get an accurate value for the temperature upon mixing. Some things to be aware of during this practical: some common errors you might be asked in an exam question, so what errors might there be using this solution calorimetry, is that you would have some heat loss or gain between the surroundings and your polystyrene cup. So even though we've insulated the best we can, there might still be some heat loss, so your reading might not be entirely accurate. This is just an approximation of the specific heat capacity of a solution. So even though we've got a value for the specific heat capacity, that value is still an approximation, so any errors in that will be carried forward to our calculations. We don't consider the specific heat capacity of the calorimeter itself, i.e. the polystyrene cup, so the impact of any heat being absorbed into the polystyrene cup. It's possible the reaction might not go to completion, so there could be some unreacted starting material left, therefore any values we use using moles of product or moles of reactants used won't be entirely accurate. And we're assuming the density of solution is the same of that of water, and whilst it'll be close, the density obviously won't be exactly that of water. So be aware of those common mistakes which you might need to state in an exam question. The other way we can measure the enthalpy change is to measure the mass of a spirit burner containing the alcohol we're going to use, and then to measure out a set volume of water and add it to the calorimeter. We would measure the initial temperature of the water, and then we would light the spirit burner. We would stir the water to try and get an even distribution of the heat. We would then extinguish the spirit burner when a specific temperature rise is seen in the water. So once we've seen maybe a rise of 40 degrees, we would extinguish the spirit burner. We would measure the final temperature of the water and the final mass of the spirit burner. This way we could determine how much fuel has been burned and what the temperature change of the water was. As in the example we've looked at a moment ago, there are some specific errors you need to be aware of with this practical. Like before, you could have some heat loss to the surroundings, which isn't considered in your calculation. You could have some incomplete combustion taking place. Some of the alcohol could have evaporated as opposed to have been burnt. Therefore, you might have a slight difference in the mass readings between the actual mass burnt. If there was inadequate stirring, your temperature change might not be consistent throughout. And again, you're neglecting the specific heat capacity of the calorimeter, so your readings might not be entirely accurate in terms of the temperature which has gone directly into the solution as opposed to into the calorimeter itself. Required Practical 3 measures the rate of a chemical reaction. You'd use a measuring cylinder to measure out about 50 centimetres cubed of sodium thiosulfate solution and put it into a conical flask. That would go on top of a white tile with a cross drawn underneath it, and you would note the initial temperature of the solution. You'd then add 5 centimetres cubed of hydrochloric acid to the sodium thiosulfate and start timing. You'd record the time it takes for the cross to disappear from view, and then record the final temperature of the reaction mixture. You'd then repeat this experiment using hot water baths or ice baths to obtain results for a range of different temperatures. You'd then plot a range of temperature against time using the average temperature change for each reaction, as you'd need to repeat each test at least 3 times. Required Practical 4 looks at inorganic ion tests. For each of the various ions, you've got to know what reagent you would use to test for it and what the expected result would be. To do the practical, you would add the reagent to a test tube containing the sample and observe the results. For the ammonium ion, you would add sodium hydroxide, gently heat it, and hold damp red litmus paper over. A positive result would be the production of ammonia gas, which would turn the litmus paper blue. The test for carbonate ions is to add hydrochloric acid. You would then see effervescence or the carbon dioxide gas being produced. You could further test for this by bubbling the gas through lime water or calcium hydroxide solution. If it turns cloudy, the gas was carbon dioxide. The test for sulfate ions is to use hydrochloric acid followed by barium chloride. A positive result would be the production of a white precipitate. The test for chloride ions, bromide ions, and iodide ions is to add nitric acid and then silver nitrate. Chloride ions would produce a white precipitate, bromide ions a green precipitate, and iodide ions a yellow precipitate. You could then test the precipitate to further identify the ion by adding dilute ammonia solution, which would dissolve the chloride precipitate, concentrated ammonia solution, which would dissolve the bromide precipitate. Concentrated ammonia solution would not be able to dissolve the iodide precipitate, so you could further identify the three precipitates by adding various concentrations of ammonia solution. Required Practical 5 is the oxidation of a substance via the distillation method. For example, you might oxidize an alcohol into an aldehyde. You'd measure out the acidified potassium dichromate solution and add this oxidizing agent into a boiling tube. You need to make sure that you are wearing protective gloves and eyewear when handling this oxidizing agent, as it is very corrosive. You'd then cool the boiling tube in a cold water beaker. You'd measure out your ethanol and add that dropwise into the oxidizing agent. You'd make sure your boiling tube remains immersed in the cold water, as this reaction is very exothermic, so the cold water beaker helps to keep it cool. You'd then pour the contents of this beaker into a pear-shaped flask or a round bottom flask and add a spatula of anti-bumping granules. The anti-bumping granules prevent the formation of large bubbles, which causes bumping, that could cause too much of your mixture to distill over in one go. You'd then set your apparatus up for distillation, as shown in the diagram. You'd immerse your round bottom flask or your pear-shaped flask in a beaker of water. Heat the beaker of water slowly until your solution starts to distill off. If needed, you could cool your receptacle, in this case a conical flask or a test tube, in cold water to prevent the loss of any ethanol as vapour. Some notes about this practical. Your thermometer bulb should be the T-junction connecting your round bottom or your pear-shaped flask to the distillation apparatus, as shown in this diagram. This means it is accurately recording the temperature at the point at which the vapour distills. If your thermometer is too far down, it's going to be recording the temperature of the lower part of the flask and not the point at which it distills over. Again, if it's too far up, the vapour won't reach the thermometer before distilling over, so you won't accurately be able to record that temperature. When you're setting up distillation apparatus with your condenser, you need to make sure water comes in at the bottom and out at the top, and that way the entire water jacket is filled with cold water. If it goes in at the top and out at the bottom, it just runs down the side closest to the bottom, as opposed to filling the entire condenser. When drawing a diagram, make sure there are no gaps between the various pieces of equipment, as that is a space where vapour could escape. If you intend equipment to be joined without a gap, make sure you draw the equipment in that way, as shown in the diagram. The acidified potassium dichromate will undergo a colour change from orange to green. You could be asked about this colour change in the exam. Required Practical 6 is a test for various organic molecules. Like the inorganic ion tests, the practical element of this is quite straightforward. You'd add the reagents to the test tubes and observe the result, but you need to know the different functional groups, their associated tests, and positive results. The test for an alkene is to add bromine water. The positive result would be the orange colour of the bromine water being decolorized. There are two possible tests for aldehydes. You can use the failing solution, which when heated will form a blue solution to a red precipitate. You can also use Tollens reagent, which when heated will form a silver mirror. Ketones would show a negative test, as these reagents work by oxidizing the aldehyde. Ketones can't be oxidized, so Tollens and Phelan's will show a negative result for ketones, but a positive result for aldehydes. To test for carboxylic acid, you'd add sodium carbonate or sodium hydrogen carbonate, and you observe effervescence, which is bubbles being formed, and that is the CO2 gas. For primary and secondary alcohols, or further test for aldehydes, we can oxidize them. So we could add acidified sodium dichromate or acidified potassium dichromate, either reagent would work. You can tell if the dichromate has been oxidized by observing the orange colour changing to green. Both primary and secondary alcohols can be oxidized. Aldehydes can be oxidized, so this test would work for any of these three functional groups. To test for a chloro, bromo or iodoalkane, you'd warm each of the solutions with silver nitrate. If you have a chloroalkane, you'll have a slow formation of a white precipitate. If you have a bromoalkane, you'll have a slow formation of a cream precipitate. And if you have an iodoalkane, you'll have a slow formation of a pale yellow precipitate. Finally, to test for an acyl chloride, you would add silver nitrate. You would not warm it in this case, as during a positive test result, the reaction is very vigorous, producing steamy fumes of hydrochloric acid and a rapid production of a white precipitate. So to tell the difference between these two possible results when we're using silver nitrate in both cases, we would not warm it if testing for an acyl chloride, and we would note the rate at which that white precipitate was formed, slow for a chloroalkane, a very rapid and vigorous reaction for an acyl chloride. Required Practical 7 looks at monitoring the rate of reaction. There are two ways this can be done. This first method looks at measuring the rate of reaction by the initial rates method. So you would measure 50 centimeters cubed of your hydrochloric acid and add it to a conical flask. You would set up a gas syringe, clamped so it's not going to fall over, and weigh out the mass of magnesium you're going to use, for example 0.2 grams. You'd then add the magnesium to the conical flask and attach the bung. Once you've done that, you'll start the stopwatch. You'll record the volume of hydrogen and gas collected within 30 seconds. You'd then repeat this experiment using different concentrations of hydrochloric acid and measure the amount of hydrogen gas collected 30 seconds in each case. This method looks at how to monitor the rate of reaction by continuous monitoring. Again, you'd set up the equipment as before, and you'd measure out your hydrochloric acid into the flask. You would set up the gas syringe as before and weigh out your magnesium. When you add your magnesium, you'll start the stopwatch, but this time you record the volume of hydrogen collected every 15 seconds for 3 minutes. You could then repeat this experiment in the same way as before, altering the concentration of hydrochloric acid each time, and throughout each of those experiments, every 15 seconds taking a reading for the volume of gas collected, doing that for a total of 3 minutes. Required Practical 8 asks you to measure the EMF of an electrochemical cell. Equipment will be set up as the following diagram shows. You'd start off by cleaning a piece of copper and a piece of zinc using sandpaper to remove any surface which might be on those metals. You would then degrease the metal using some cotton wool and propanone. You'd place the copper into a 100ml beaker with about 50 centimeters cubed of 1 mole per decimeter cubed copper sulfate solution. You'd place the zinc into a 100 centimeter cube beaker with about 50 centimeters cubed of 1 mole per decimeter cubed zinc sulfate solution. You'd then lightly plug one end of a plastic tube with cotton wool and fill the tube with a solution of 2 molar sodium chloride. You'd then plug the alternate end of the tube with cotton wool and join the two ends of the beaker with this inverted U tube. So therefore we've made a salt bridge between the two beakers. You'd connect the half cells by connecting the metals using crocodile clips, attach them to a voltmeter and read the voltage of the cell. Required Practical 9 uses titrations to investigate how the pH changes in a weak acid, strong base titration and a strong acid, weak base titration. The first part of this practical is to calibrate the pH meter by measuring the pH of known buffer solutions. This is necessary because pH meters can lose their accuracy after they've been stored. To do this, you'd record 3 buffer pHs and their actual values plotting a calibration curve. So for example, if you've got a buffer solution of 5.5, but the pH meter read 5.2, you'd plot those points on the calibration curve, repeat for 2 other known buffer concentrations, join them with a line of best fit, and therefore you've now got a calibration curve so you can assess the reading given on the pH probe with what the actual pH should be. Once you've done that, you can begin the practical, in which you'll measure the initial pH of the alkali being used. You'll then add acid in a small amount, noting the volume added each time, stir the mixture each time to equalise the pH, then measure and record the pH to 1 decimal place. When you approach the end point, you'll add your acid in much smaller amounts, continuing to stir and record the pH at each point, and repeating this process until the acid is in excess. This will allow you to generate a titration curve, during which you should see a vertical endpoint. You could improve the accuracy by maintaining a constant temperature throughout this practical. Required Practical 10 involves producing a pure organic solid and testing its purity. There are various ways in which you might end up producing an organic solid. We're now going to have a look through about how we could purify it. In the exam, you've got to give the different steps and the reasons for those steps as to how you could purify an organic solid. The first thing to do is to dissolve the impure compound in the minimum volume of hot, so near boiling, solvent. An appropriate solvent for this is one which will dissolve both the compound and any impurities when hot, and one in which the compound will not dissolve well when it is cold. We use the minimum volume of hot solvent to obtain a saturated solution and to ensure that the crystallization of the pure product will occur on cooling. This will increase the yield. We then do a hot filtration of a solution through filter paper, and we do this quickly as soon as it is dissolved. This will remove any insoluble impurities, and the heat prevents the crystals from reforming during filtration. We then cool the filtered solution by inserting the beaker into some ice. The crystals will reform, but any soluble impurities will remain in the solution because they are present in small quantities, so the solution is not saturated enough for them to crystallize out. Cooling and using ice will increase the yield of the crystals. We then use suction filtration with a Buchner funnel to separate the crystals from any remaining solution. To do the suction filtration, we connect a water pump to the Buchner flask. This reduces the pressure inside the flask and speeds up the filtration process. We then compress the crystals inside the Buchner funnel. This allows the air to pass through the sample rather than around it, so we've got a thin layer of crystals covering the filter. This means that they will dry better. We then wash the crystals with distilled water to remove any insoluble impurities, and we then dry the crystals between absorbent paper. For example, we might use some filter paper. This ensures that water is not left on the crystals, which would then cause the measured mass to be greater than the actual mass. Some notes about this practical is that you might lose yield from losing crystals by filtering and washing, the product staying in solution after recrystallization, so not all of the dissolved product turning into crystals, and you might get various side reactions taking place. We can then measure the melting point of the sample by using an electronic melting point machine, in which you put a small amount of the salt into a capillary tube and then heat this up, heating it slower as you reach the expected melting point. A pure sample will have a sharp melting point at the same value quoted in the data books, so it will melt at the precise temperature quoted. If impurities are present, the melting point will be lowered and the sample will instead melt over a greater range of temperatures. So for example, it might melt from 210 to 220 degrees rather than melting at precisely 215 degrees. The second part of Required Practical 10 is how to prepare a pure organic liquid. In this case, for the reaction you are doing, you'd heat the solution and the reagents under reflux conditions and then allow them to cool. you'd then put your distillate of your impure product into a separating funnel. We wash the product by adding sodium hydrogen carbonate solution, shaking and releasing the pressure as CO2 will be produced from the hydrogen carbonate. We then allow the layers in the funnel to separate, and then run and discard the aqueous layer. We then run the organic layer into a clean, dry conical flask and add 3 spatulas of drying agent, in this case anhydrous sodium sulfate. This will dry the organic liquid, so removing any water trapped in the organic layer. We would then decant the liquid into a distillation flask. We would then distill to collect the pure product, just like we would do in required practical 5. Some notes to this practical is that a reminder that reflux is a prolonged heating of a solution, allowing any solution which evaporates to be returned to the reaction mixture. Anti-bumping granules should be added to the flask during reflux to prevent vigorous boiling by allowing smaller bubbles to form instead of larger ones. Sodium hydrogen carbonate neutralizes any of the remaining acid, and the sodium chloride will help to separate the organic layer from the aqueous layer. The drying agent, to remove any of the water left in the sample, needs to be insoluble in the organic liquid and not react with the organic liquid, as we don't want any side reactions taking place. Required Practical 11 involves carrying out test tube reactions to identify transition metal ions in solution. The practical steps to this is to measure out 3 samples of each unknown metal ion. To the first, add a few drops of sodium hydroxide solution, and then carry on adding sodium hydroxide until it is in excess. To the second test tube of the sample, add a few drops of ammonia solution, and then keep on adding until it is in excess. To the third, add a few drops of sodium carbonate solution. For each of the possible metal ions, you've got to know what kind of precipitate they would form with each of the different reagents. Our copper ions would form a blue precipitate in hydroxide ions or ammonia ions. They would have no visible change when excess hydroxide is added. When excess ammonia is added, you'd form a deep blue solution instead. With the sodium carbonate solution, you'd form a green-blue precipitate. For our ion solution, we would form a green precipitate when we add hydroxide or ammonia ions. There'd be no visible change with excess hydroxide and no visible change with excess ammonia. When we add sodium carbonate, we would observe a green precipitate. When we look at our aluminium solution, we would have a white precipitate when we add hydroxide or ammonia ions. We would have a colourless solution with excess hydroxide and no visible change with excess ammonia. Our carbonate solution would produce a brown precipitate of bubbles, and this would be carbon dioxide. Our iron 3 solution would form a brown precipitate when we add hydroxide or ammonia ions. Excess hydroxide would show no visible change, and excess ammonia would show no visible change. When we add sodium carbonate, we'd observe a brown precipitate and bubbles of carbon dioxide being produced. Required Practical 12 involves doing chromatography. This could be of amino acids, or it could be of a small sample of medication, for example, paracetamol and aspirin, and seeing if they are together in a combined drug. The method will be the same regardless of the chemicals you are testing. The first step is making sure you are wearing gloves to draw a pencil line above the bottom of the TLC plate and mark spots for each of the sample equally spaced along the baseline. We use gloves to prevent contamination from your hands. We use a pencil as that will not dissolve in the solvent. We then use a capillary tube to add a small amount of each solution to a different spot and allow the plate to dry in air. If we use too big of a spot, this could cause 2 different spots to merge. We then add the solvent to a chamber or large beaker with a lid so that it is in no more than 1 centimetre in depth. If the solvent is too deep, it will dissolve the sample spots from the plate and the practical won't work. We then place the TLC plate into the chamber, making sure the level of the solvent is below the pencil line and replacing the lid so there's a seal on top. Again, we need to make sure that the pencil line is above the level of the solvent so we don't dissolve the spots into the solvent, and a lid will prevent evaporation of the solvent, which is especially important in case you are using a toxic solvent. When the level of the solvent reaches about 1 centimetre from the top of the plate, remove the plate and mark the solvent with a pencil. You'll get more accurate results if the solvent rises to the top of the plate, but you can calculate RF values regardless. You then allow the plate to dry in a fume cupboard, and a fume cupboard must be used if the solvent is toxic. You then calculate the RF values of the observed spots. You need to be aware that for this practical, the amino acids, or other chemicals you might have done chromatography on, can be colourless. This means you need to develop the spots so you can see where they are, so you can calculate the RF values. To do this, you can either spray the plate with a chemical called ninhydrin and heat it for 10 minutes, and that will cause red-blue spots to appear. Alternatively, some TLC plates have got a fluorescent dye coated on them, so spots can be seen if you put the plate under UV light. You could also place the plate in a beaker with iodine vapour, and the iodine vapour will stain the spots purple. Each amino acid or each chemical will have a unique RF value.